let's look at on the graph. So what we are seeing here, we are looking at the sigma or a stress and a strain graph. All right. So different type of concrete, high strain concrete, normal strain concrete, right, is the middle one, and low strain concrete. All right, as you can see, their F prime C is different. The F prime C of this one is here, for this one is here. For this one, it is hard to say. I don't know, it just should be around here, right? Because it's corresponding to this strain. All right. So the F prime C, as we discussed, it is coming from 28 days test. Okay. Let's see, let's just read a couple of other information. As we said, as you can see here, so this number 0.02 strain, it is corresponding to F prime C, no matter what, how much your F prime C is. Usually this is how much deflection your concrete can take to reach you to F prime C. How much strain you can take, all right? So I'm gonna write under it that corresponding to F prime C, correct? Now, this number also would be interesting, 3,000. That's, if you remember, I told you we are losing the concrete, right? Okay. So as you can see, the concrete is not totally, the material is not crushed truly. It is still continued. Look at this, guys. This guy here, this guy here, and this guy here. All right. So the concrete is still there, is not crushed. So this is a portion of the curve neglected by the ACI code. So we don't care about it. We assume that it is gone totally to be conservative. It is being conservative, right? Although the concrete is not totally gone, we assume it is gone. Conservative. Although it is not totally gone, but we assume it is gone because we would say, all right, it wouldn't work anymore. So although it is still there, but we would say it is gone. So it would be conservative design, conservative assumption for our design. All right. And what else? As you can see, something happening here. As the strength goes up, as the strength goes up, what is happening? If you think about it, modulus of elasticity of concrete is going up, right? Because if you think about it, the E, which is the slope of a linear region, all right? Remember this? What was the modulus of elasticity? If you remember, that was the slope of linear region. It would be going up. But another thing is happening. The deformation getting lower. You are seeing less deformation, right? As you can see, the tail, this tail is just getting closer to you, right? It shows what? It shows the deformation getting less. It deformed less. So we can associate that with the ductility. So we can say ductility is getting less as well. All right. That's another observation that we can study here. Okay. Let's continue. All right. Modulus of elasticity of concrete. We gave an introduction for it already, sort of like a reminder per se. So there is no clear cut for modulus of elasticity of concrete. Okay. Depends upon which modulus definition is used. You can use initial modulus, tangent modulus, secant modulus, secant modulus, or long-term modulus. All right. You can define the concrete modulus of elasticity. Again, why it is hard to define? Because it is a very thin material. The stress strain diagram is not pretty known. Let me show you one more time. All right. This is your prime C. Okay. So where would be your modulus of elasticity, as you know from your mechanics of materials? This would be the slope of linear region. That is just the official definition, right? Meaning what? Meaning this slope here would be the modulus of elasticity. All right. So different methods we have for finding the modulus of elasticity. AECI uses the secant modulus, the slope of the line drawn between the origin and a point on the curve, normally at 0.45 F prime C, will be used for that. All right. Look at this. So you're going to read the slope of a line. Let me use purple probably. That goes from origin. So if it is F prime C here, 0.45, for example, if it is here, this is 0.45 F prime C. Okay. So the slope of this line, if you draw a straight line between these 2 points, so the slope that you're reading from here would be modulus of elasticity of concrete. That is how you get it. So 0.45 in a way would be your threshold to be linear in a way, if you think about it. That is the assumption. It says 0.45 is just, it is a still linear up to this point. All right. From excuse me. This 0.45 will be used also in some calculations. I'm going to talk about it momentarily. All right. So from this code reference, that's just a basically provision in the code that you are supposed to obtain. And there have been questions, but I'm emphasizing again that you want to have pounds inch units, the American units. So we should obtain that. From this provision in the code for units weight from 90 to 60 PCF. So this is what? This is the WC, or concrete density. So for this concrete density between 90 to 160, this is the formula you will be using to find the modulus of elasticity. WC, which is the weight of concrete in terms of PCF units, pounds per cubic foot. Sorry. All right, PCF, pounds per cubic foot. W is to the power of 1.5 times 33, a square root of f prime c. F prime c in terms of PSI. You need to apply in terms of PSI. Okay. Also, as another estimation that it is very commonly used because, well, the concrete usually hovers around this for its density, 145 for normal weight concrete. So if you plug in 145 for this terms WC, because this factor would be 57,000. So easily you can say, all right, 57,000 is square root of f prime c. Okay, so that would be another way to find it, which is for normal weight concrete. But this is the general formula. The top one is the general. All right. I want to give you a note here. In the ACI code, you are seeing this term a lot, right? Whenever you see this f prime c needs to be entered as pounds per square inches, PSI. All right. That is something you're going to see a lot, a square root of f prime c. So whenever you see that, f prime c needs to be plugged in terms of PSI. Okay. All right. So let me see here. And the answer you get by applying PCF for this one, PSI for this one, the answer you will get would be in terms of PSI for the E. All right. It is not from the formula for the, I would say, consistency of units. It is not making sense, but it's just practical formula. So you want to make sure that you're plugging the numbers correctly, and the answer you're going to get for EC, if you plug everything, as I said, it's going to be in terms of PSI. Okay. So let's continue. All right, so tensile strength. It is about 10 to 15% of compressive strength. All right, so what does it mean? So technically, if it is your cylinder, if you push it, right, with F prime C, you're going to break it, right? If you have the same cylinder, if we pull it and break it, right? Let's say you're going to break it with something called FT, tensile strength, all right? Here we are saying that your FT is almost 10 to 15% of F prime C. Much lower, right? Much lower. Your tensile strength is much lower than compressive strength. Generally neglected in flexion and axial strength calculation. So sometimes, and a lot of times I would say, this tensile strength, which is low number, small number, it would be totally ignored. And we wouldn't count on the tensile strength of concrete at all. So that would be something we ignore from the first place. It would be conservative again. So other components will take care of the tension. We're going to talk about it. Two definitions are used in some formulas for normal weight concrete. All right. So there is an estimation to find the tensile strength of concrete is coming from this formula, all right, from the code, the reference given, 7.5 lambda f square root of f prime c, where fr is the modulus of rupture, which is giving you the tensile strength in flexure. So tensile strength, but mainly in flexure, can be found by this formula. All right. So again, f prime c on this formula, you know that it is in terms of psi because it is under the square root. So this FR, really this FT I'm talking about, the tensile strength. But since it is talking about the rupture modulus specifically for flexure, we are showing with FR. So rupture modulus shown with FR, it is really the tensile strength in flexure. All right. So again, these are estimation, these are practical formulas. This lambda, it is an index for concrete weight. All right. So it is in 2.4.2. So lambda is equal to 1. And it goes from 0.65, 0.75, or 0.85. All right. So it is 1 for normal weight concrete. Let's just write it one more time. Normal weight concrete. All right. These three are for lightweight concrete. All right. It is the three different numbers because it depends on what type lightweight concrete you are dealing with. You got to look at that code, but if it is sand-based, this would be the one we're going to select. But if it is not sand-based, again, we're going to have different scenarios. Okay. I think it is 0.65 as well. Now I'm a little bit dot at this moment. I think, well, I'm sure about 0.75, 0.85, but 0.65 maybe. I gotta double check that. All right. So if it is normal weight concrete, it's straight 1. You're gonna apply it here. FR, you're gonna find it. All right. Another way to estimate the tensile strength of concrete, it is coming from a test called a split cylinder tensile strength. This is another test. It can give you tensile strength of concrete. It is shown with FCT, but again, it is FT indeed with the specific method, which is a split cylinder tensile. We're going to talk about this further. What is this test that it's giving us a tensile strength of concrete? All right. So tensile strength 10 to 15%. There are ways to estimate the tensile strength of concrete. Shear strength of concrete, it ranges between 1/3 to 4/5 of ultimate strength of concrete. Again, so shear strength would be different story again. It would be between 0.33 to 0.8. So it can be just like different values. Depends on really what type of concrete we are dealing with. It is very difficult to obtain a good test for shear strength. In typical concrete structure, pure shear strength of concrete, well, it is not really the sentence I like. It can be an important thing. So I would say, in terms like we can work with the shear friction concept that if we get a time, we're going to talk about it. It is just dealing with the pure shear. So it has its own story, but we are trying to say that shearing a strength of concrete, it would be a topic itself. This is the interval for it. And we're going to look at how to estimate it in the next sessions. All right. So let's continue.